Hello, I am Yan Dai, a first-year PhD student at the Operations Research Center of MIT. I am excited to introduce adversarial network optimization under Bandit feedback, a joint work with Professor Nongbo Huang. Stochastic network optimization, or SNO, is incredibly successful in allocating resources for dynamic networks, but it assumes ideal conditions like stationary environments and full pre-decision information. However, real-world networks can be pretty different. They can suffer from non-stationarity due to mobility or attacks, and we can study adversarial networks. Real-world planners often also make decisions in blind and only learn from limited post-decision feedback. We capture this by Bandit feedback model. We also consider general and complex multi-hop topologies, as well as the utility maximization task. To summarize, in our problem, the planner faces a general multi-hop network system. The planner decides arrival rates to each server without knowing the current utility function. This further introduces multiple interdependent queues on each server. The planner also decides routing plans without knowing link capacities. Finally, even after decisions, the planner is still only able to see the actually collected utility, hiding any counterfactual information. So how do we tackle this? We call our approach online learning for adversarial network optimization, which is framed within 3 steps. The first step is reducing the complex network problem to online learning via a global Nearplov analysis. That is, instead of considering a single Nearplov term one by one, which is typical in SNO, we consider their sum in a whole for more robustness towards adversarial corruptions. In our case, we reduce the utility maximization task to 2 online learning problems listed here in red boxes, namely OLO and BCO. Second, network problems also present unique challenges. For example, since network queues do not allow uniform length upper bound, this results in unbounded loss magnitudes in online learning. Therefore, we design novel queue-based online learning algorithms, an OLO algorithm called ADA-PFOL for routing, and a BCO algorithm called ADA-BGD for arrivals. They are adaptive to these network specifics. Finally, we use a self-bounding analysis to translate the online learning performance guarantees back into network guarantees for both stability and utility. An example of such analysis is highlighted in gray here, and we direct the readers to our paper for more details. This gives our overall algorithm UMO square, where UM stands for utility maximization, and O square means the 2 optimization we adopt. As we sketch, our algorithm UMO square achieves 2 critical guarantees simultaneously. First, it ensures network stability, namely the average queue length in the system remain bounded, preventing congestions. Second, it also delivers near optimal utility, which converges to that of any mildly varying policy in a polynomially fast speed. This mildly varying policy may depend on the full game trajectory, that is future information, or it can also optimize over some information that is not revealed to our online planner. So UMO square is the first algorithm providing utility guarantees for complex adversarial multi-hop networks and operating under any bandit feedback. Meanwhile, we introduced the general reduce, design, and extend framework for solving ANO problems via online learning techniques. Finally, we also contribute novel and adaptive OL algorithms that can be of independent interest. Thank you very much for your listening. This page summarizes the main contributions and takeaways of our paper. More details can be found in our full paper, and you are more than welcome to reach out if you have any questions. Thank you.